And then the cells of the nervous system, you remember we did like the oligodendrocytes and astrocytes and ependymal cells. Where they're located are the central nervous system or peripheral nervous system, right? We talked about which ones form myelin in the peripheral nervous system, which ones form myelin in the central nervous system. We talked about diseases, multiple sclerosis, Guillain-Barré disease, which causes demyelination, one from the peripheral, one from the central. And then we talked about resting membrane potentials. Andrew. Resting membrane potentials, how resting membrane potentials were established, right? More potassium on the inside, more sodium on the outside, sodium, potassium, ATPase, and potassium channels. So any of that you want to go over, I'm happy to go over. We can. Resting membrane potential?
Yeah.
Okay. So we did this in class. There were three different types of membrane proteins that we needed to establish a resting membrane potential, right? Now, first thing we did was set up a gradient. What's the most abundant cation inside a cell? Potassium. What's the most abundant cation outside a cell? Sodium. All right? Now, we're going to establish a resting membrane potential. Do you remember what the resting membrane potential is that you find in your average neuron? Negative 70 millivolts, close, right? So 90 is an important number, right? So how do we get this gradient established? What causes there to be low sodium inside and more potassium, and low potassium outside? Remember what we did to get this difference across the membrane? We had to have a pump, right? So we're going to pump potassium in, right, because you got more on the inside. And we're going to pump sodium out, right? What do we have to power the pump? If you're establishing a gradient, we have to have ATP, right? We have to have some kind of energy. So we're going to use ATP, convert it to ADP. And you can think of this as kind of keeping your room clean. You have to put input energy to keep all your clothes inside the drawer in the closet. If you don't input energy, you're going to get stuff randomly distributed, right? And this is not random. Having more potassium inside, less potassium outside, that's not random, right? You have to put energy in to maintain that, right? Then, so now we've got our gradient set up, right? So the next thing we added were passive channels, right? Do you remember passive channels? Right? Do they close at all? Never. Never close. So we're going to have what are called leak channels or passive channels. And the first type of channel we're going to put in is for potassium. So this is a passive potassium channel. They're always open, right? So which way is potassium going to move? Out, right? So we're going to have potassium moving out. What will that do to the inside of the cell as far as charge goes?
Negative.
It becomes negative, right? And so if we're moving lots and lots of potassium out, this is your number. Yeah. If we only have potassium channels, right, we end up with a resting membrane potential of minus 90 millivolts. If we only have potassium. So we've got to add something else to get to our minus 70, right? So what we're going to do is we're going to put in a few, not as many as potassium, right? Potassium is a major player here. We're going to put in a few sodium channels. So this is our passive sodium. Which way is sodium going to move? In, right? Because you got more outside, less inside. It's going to go down its gradient. So it's actually going to go in. What's that going to do to the charge inside the cell? More positive, right? And so what that does is it starts out at minus 90, right? And it's going to increase to minus 70. Minus 70 is more positive than minus 90, right? This is closer to 0. Okay? And that's due to the movement of sodium, right? So what is having the major influence on resting membrane potential in a neuron? What's the major player? Potassium, right? This one caused this much change in the membrane potential, right? Sodium only caused plus 20 millivolts, right? That's small compared to minus 90, right? So potassium is a major player. You have 100 times more potassium moving than you do sodium. You only have a little bit of sodium, but it is enough to move you to minus 70 millivolts from minus 90. Okay? So what are the three proteins you need? Sodium, potassium, ATPase, passive potassium channels, and passive sodium channels. Those are the three proteins you have to have in the membrane to establish this resting membrane potential. Right? The pump establishes the gradient. The gradient determines which way ions are moving through the passive channels.
So at what point is the cell starting to get like hyperpolarized?
Say that part again?
Like hyperpolarization.
Hyperpolarization. Okay.
There's that one question, and that's what I got confused on the negative 90 about.
Okay. So this is in a resting neuron.
Okay.
Right? Resting neuron. We're not dealing with voltage regulated channels, chemically regulated channels, or mechanically regulated channels. Right? In an active neuron, which is not on this test, right? You can open up voltage regulated potassium channels. Right? And when you do that, they stay open a really, really long time and you overshoot resting. Right?
Yeah, there's that question that says hyperpolarization of a neuron will shift the membrane potential towards what? 0 millivolts, negative 90, negative 70.
Okay, so yeah, that's just definition. Okay? So here is 0. Right? And here we're at minus 70 millivolts. Right? So this is where we start out with. Depolarization is you're getting closer to 0. Hyperpolarization, moving away from 0. Okay? So depolarization looks like that. Hyperpolarization, like that.
So it is negative 90.
It is negative 90, hyperpolarization. Yeah. Yeah, that's just definitions. And if you think about being polarized, right? If you were making something depolarized, the difference is going to be 0, right? Everybody's the same. Hyperpolarized, you're moving to a greater difference. So you're moving away from 0 difference.
So with hyperpolarization, would it be negative 70?
You start out at minus 70 in an average neuron.
Well,
Hyperpolarization will drop it, move it away from 0. Right? You'll drop it. It'll decrease. Right? And making the difference bigger between inside and out.
So what would it be with repolarization?
I didn't. The way the question was phrased, I didn't ask it that way. Repolarization is you're going to go to resting. So it's the downhill slope of an action potential. That's repolarization. There's hyperpolarization, depolarization. Okay, and this is not on your exam. This is the action potentials are not on your exam. Depolarization, hyperpolarization. You should be able to answer those questions.
Yeah.
Towards 0, away from 0.
Yeah, I was thinking of that too.
Yeah.
So none of this stuff goes.
None of that can be on there.
So for this question, you basically wanted that.
Yeah.
I
wanted you, yeah. Right, so, I mean, it's how do you establish a resting membrane potential, right? You need 3 proteins, right? 3 membrane proteins. Sodium, potassium, ATPase establishes the gradient. Potassium channels, passive potassium channels. Potassium goes out, making the inside of the cell more negative. Sodium, passive sodium channels, a little bit of sodium creeps back in, bringing it to minus 70 millivolts. Yeah, and that was what I was looking for. All right, other topics. know what you need to know on that. Yeah.
Do you know like an easy way to express something stupid, but like the motion of each joint, like?
Sure. Okay, so extension is you're making the angle bigger. Flexion is you're making the angle less. All right? So I'm at 180 degrees. Right? I'm a line. Right? Flexion. Flexion. Right? I'm no longer a straight line. Extension, straight line. So straight line, 180 degrees is extension. Okay? Flexion, I am less than 180. I don't know what that would be. 120. You guys okay?
So pointing your leg up like this is
Flexion.
that's flexion?
Yep.
What do they call leg extension? That's not cool.
Can't help you.
Yeah.
Extension, so when you are, so bringing your hip back is extension, hyperextension, greater than 180 degrees.
Hyperextension, so you're
Right?
making the angle bigger.
Making the angle bigger. Okay? So that's, okay, how's it going?
When
All right.
you were in a straight line, that
I
was
was in
extension.
That was extension. Right? Flexion, your arms coming forward. Flexion, your legs going forward. Right? Hyperextension, going further back. And some joints won't do that. You will break a joint if you try that with your knee.
Yeah.
Right? Then 180, flexion. So when you bend your knee, that is flexion. You're no longer 180, right? Bend the elbow, flexion. No longer 180.
This is getting so easy.
Okay. I'm glad.
So like pointing is flexion.
Flexion, hands down, extension. All right? Then adduction,
Yeah.
abduction, right? Abduct, you take away. Adduct, you add back. Abduct, you take away. Adduct, you add back. All right? Then you've got supination and pronation. Sup, you're holding soup, right?
Yeah, that was pretty good.
And pronate, soup. Right. All right. And then what about standing tippy toe? Plantar flexion, heels in, dorsiflex. You got it. All right. So it's, or did I help at all? You good on?
What was the last one? Not plantar, but
Dorsiflexion is heels in, tug of war. Tug of war.
Cool.
Heels in.
Dorsal.
All right, so can you do the sheet then? You'd be okay to do that sheet that I gave you? What sheet? This sheet?
Yeah.
You got that? Yeah. What was that? All right. So you guys okay with that sheet? You guys can figure it out at least?
Right here, bro.
All right, so you guys okay with the articulation worksheet? That if you go over that, you'll be in really good shape for articulations. All right, you know how you've labeled the eye and the ear. You're good with labeling eyes and ears, right? You can do a muscle sarcomere, right? Z-line, M-line, thick filaments, thin filaments. You know the structure. You know what they're made of.
I still get confused with that.
Huh?
The when it gets bigger, and I get confused about that too.
Okay.
What's that saying? You know what that means. Like a dolphin.
Yeah, that was, if you look at exam 3, there was this exact question on it. That exact question on it. So yes, that will be on you. All right, so we've got a sarcomere. And what you've got to remember about the sarcomere is that it's a repeating unit. So you've got a sarcomere on this side, you've got a sarcomere on this side, you've got another one on the other side. What happens in one is going to happen to all of them. So if the one gets bigger, they're all going to get bigger. If one gets smaller, they're all going to get smaller. Okay? So the way that this works is that you've got thin filaments, right? And the thin filaments, if you view this like as a wall, right? Thin filaments are coming out from the wall, pointing towards the center, right? Then we've got thick filaments. That sit in the center of the room and reach out to the side, okay? You've got a line that runs right down the middle, the M line, right? M is in the middle, okay? We've got thin filaments. These are made up of actin. That's your pearl strand, right? Talk about having a strand of pearls. That's what that is. Thick filaments are made of myosin. Myosin with a two-headed golf club, right? You have to have the head that pivots. Okay? So we've got the boundaries, which are the Z lines. So the M line holds the thick filaments. The Z lines define the boundary of a sarcomere. Start and stop at the Z lines. And these anchor the thin filaments. Okay? Now, we said that the so you've got A band, I band, and H band. Okay? The A band never changes in size. Never changes. If you have your grade is an A, you don't want it to change, right? Never changes in size. And that's because it's this thick. Right? That doesn't change length ever, right? That thick filament is never going to change size. It's going to be right there in the middle, right? Not changing size. Okay? Then you've got, you said that you have sarcomeres on the other side, right? What letter does this look like? I. Okay? When the myosin grabs the thin filament and pulls that to the center, right? This distance is going to get shorter, right? So that I band will shrink, okay? Because what's going to happen is this thin filament is going to move towards the center, right? Pulling the Z line towards the center, right? So this whole deal is going to move. So this distance is no longer that long. So we shrunk that. Then the gap in the middle is the H, right? So from the end of one thin filament to the end of another thin filament is H. Well, if we're pulling those towards the middle, what's going to happen to that gap? It gets smaller. So these two to help you. It wasn't the test session. Okay. What else?
Oh, you know what you do it like the cylinders, like I know the definition of them, but
Okay.
you know how you have on that sheet, like the cubic synthesis, like what kind of
Oh, what kind is, which kind is which?
yeah. So like
Logically, you should be able to figure them out.
yeah.
Okay? So diarthrotic is freely movable. Right? Freely movable, right? Pubic symphysis is where your two pubic bones come together, right? Do you want that to be freely movable? No, right? You don't want your coccyx bones to be doing that, right? That would not be a good thing, okay? Not at all. So you know that that can't be true, right? Now, the other two are immovable and slightly movable, right? Anyone who's had a baby knows that you do not want completely immovable coccyx bones, right? A little painful, right? So it has to be slightly movable, right? It has to be slightly movable, right? So, I mean, I would try to logically think through it. So, epiphyseal plates, right? That's where your bones are growing. And you have that cartilage plate right there. Yep. Do you want that freely movable? Do you want it even slightly movable? Immovable? Because it's a bone, right? You want it to kind of all hang together and not move, right? So I would do logic. I think I would do logic on that one. Distal end of your fibula and tibia. You want that freely movable? No. Do you want it immovable? Twist your ankle. Twist your ankle, right? Your tibia and fibula are moving slightly when you do that. Okay? Alright? So, do you want your parietal bone moving relative to your frontal bone? Ever? No. Right? You're encasing your brain. You don't want moving parts encasing your brain, right? You want a solid mass of bone surrounding that really delicate tissue. So sutures of the cranium, immovable. Okay.
It says trace the pathway for hearing to the final destination in the brain. How is the information about intensity of sound conveyed? Then you got a question mark, then you got pitch.
Yes. Right. Okay, so say the first part of the question again.
Trace the pathway for hearing to the final destination in the brain. How is information about intensity of sound conveyed?
Okay. So that's your ear, right? Gonna enter the sound waves will enter the auricle. Auricle's your big phone, right? Gonna capture sound waves. Sound waves will travel down the external auditory meatus. They will hit the tympanic membrane. Tympanic membrane vibrates, right? Starts moving back and forth. Sitting on the tympanic membrane, you have the ossicles, the ears of the bone, malleus incus stapes, right? What does the stapes sit on? The malleolus sits on the tympanic membrane. What does the stapes sit on? The other side.
The window.
The oval window, right? Oval window is a membrane. When the bones move, what's going to happen to the oval window? It'll start moving too, right? You remember this is where we amplified the signal? Right? So our oval window is now going to... Tympanic membrane moves 1 micron, right? That's taking the thickness of a penny and dividing it by 1,000, right? Oval window moves 22 microns. We have amplified the signal 22 times. Okay? We get to the oval window. Oval window. Okay, so external ear, middle ear, inner ear. What's different about the inner ear?
It's
Fluid filled. So on the other side of the oval window, we've got fluid. What's going to happen to the fluid? The oval window's moving? Waves, pressure waves, right? You're now changing the liquid, right? that run through the cochlea, right? Remember our snail? Right? And remember that had 3 ducts, one of which contained our hearing apparatus, the spiral organ. When those waves travel through, the basilar membrane will move up and down. Sitting on the basilar membrane you have hair cells, right? Those are our little hair cells. When this moves up and down, the hair cells hit this membrane on top, pectoral membrane, and those hair cells become bent. What happens when we start bending hair cells? We generate action potentials. What type of receptors do you find on hair cells? Chemically, voltage, or mechanically regulated? Mechanically regulated because you're bending them to trigger action potentials. All right? So coming out of those hair cells, you have ganglion, which leads to cranial nerve 8. Right? Cranial nerve 8 is your vestibulocochlear nerve. Here, okay, you guys are looking like you've never heard of this before. You're starting to freak me out. Alright? Does it sound familiar? We talked about it in class. Right? We talked about this in class. Right? Cranial nerve 8, where does that run? What lobe? Vestibulocochlear nerve. Where is that going to send information? What lobe of the cerebral cortex? What lobe sits below your ear? Temporal. Temporal lobe, right? Your ear sits on your temporal lobe, right? We're going to send information to the temporal lobe. Okay?
Would there be questions about like what, kind of like with the cerebral cortex, about where that information will register, like the high pitches and low pitch,
right? And so what does so where in the temporal lobe codes for pitch? It would be lateral side, medial, right? Because the lobe, you're kind of going into that lateral fissure.
Lateral side, lateral fissure. Yeah, that's the pitch.
It's where in the temporal lobe
Where it's
will code for pitch.
the lateral fissure.
Is it medial or lateral? So there's a lateral side and a medial side. And that codes for pitch, right? What codes for intensity? How loud the sound is. What codes for intensity of pressure? Frequency of action potentials. That's still gonna, that hasn't changed, right? That answer has not changed, no matter. So that's going to code for the frequency of action potentials codes for how loud the sound is. If it's a really loud sound, what's going to happen to the frequency of action potentials? It's going to go up. Sound gets quiet, frequency goes down.
So high pitch is on the medial side, and then low pitch is on the lateral.
Okay, the low pitch is what?
Low pitch goes to the lateral side of the temporal lobe.
Okay. And high pitch goes to the
Medial side.
Okay.
Alright, so what are the units for pitch? Hertz. Okay, so do you know your range of hearing? What's the high pitch? Yep. 3,000 hertz. If I gave you what is that telling you? Decibels is sound pressure, right? So this is going to be really high. You can hear from like 0. Right, so this would be really, really loud. Right. Like I said, there's a lot of questions on special senses. There's a lot of questions on special senses. So make sure you study special senses. Study everything, right? But make sure you study special centers. You've never been tested on that, right? You've never been tested on it, so you're pretty much guaranteed that there's about a third, I think about a third of the exam is special centers.
Is the key for the third exam still online?
It should still be up. It should still be up. All right, what else? What else you got?
Can you go over stuff that we should know from the muscle section?
Muscle section? Okay. Okay, couple things. You will want to know the process, how you get a muscle to contract. All right? You will want to know the different types of muscles, slow twitch, fast twitch. Remember, we talked about motor units, the neuron controls what type of muscle you have. If it's in the same motor unit, all those muscle fibers are going to behave the same way. So you need to know these kind of characteristics of the different types. All right? And then we talked about isotonic, isometric. We talked about complete tetanus and incomplete tetanus.
Yep.
You're welcome.
Okay, so process, right? You've got a neuron sitting on a muscle, right? What is this called? Yeah, it's a synapse, it's a particular type.
Presynaptic.
Neuromuscular junction, right? Okay. What type of neurotransmitter is in the neuron? Acetylcholine. We've got acetylcholine receptors. These are our nicotinic cholinergic receptors. Remember we talked about it in the last test, we talked about muscarinic receptors, we talked about nicotinic receptors. These are nicotinic receptors. Okay? When acetylcholine binds to nicotinic receptors, what happens to our membrane? What's the membrane of a muscle cell called? Sarcolemma. Right? What happens to our sarcolemma when acetylcholine binds to the acetylcholine receptors? It what? It depolarizes it, right? So depolarizing, getting closer to zero, right? You're getting closer to zero, right? What type of ion would have to move to depolarize a cell? Sodium, right? So this actually opens up sodium channels. Right? You got sodium going in, you're going to depolarize, and what you're going to do is you're going to trigger that muscle to undergo an action potential. And it's an action potential that causes the muscle to contract. Okay? Now, this action potential is actually going to travel along the sarcolemma. How does the action potential get to the center of the muscle fiber? The T-tubules. So that action potential will travel down the T-tubules. Right? What sits on either side of the T-tubules? Sarcoplasmic reticulum. What is contained within the sarcoplasmic reticulum? Calcium. So when the action potential travels down the T-tubules, it is going to cause the SR to release calcium. Okay? We've got two regulatory proteins that are part of our myofibrils, right? Or thin and thick filaments, right? We had tropomyosin is going to do what to myosin? Block. Right? So tropomyosin blocks myosin. Right? How do we get tropomyosin to move out of the way?
Calcium.
Calcium will bind.
And then move it, appropriate movement.
You should put in like little nails, like, you know, like the little, like,
Little pegs.
yeah, like,
Yep. And then this is the long rope. Right? So once this binds to calcium, it's going to push tropomyosin out of the way, and our thin and thick filaments can then interact. Okay? You guys okay so far? More or less? Okay? There's a couple of Khan Academy videos posted up under the muscle where you can see this. Okay, so where you can see it. If you like watching videos, the Khan Academy ones are good, and I think there's a couple others posted that show you muscle contraction. Okay, so now our thin and thick filaments can interact. All right, so here's myosin. We said a two-headed golf club, and the head pivots. Right, head's going to move. What makes the head move? ATP. All right, so to get myosin to bind, right, you have to have ADP and inorganic phosphate bound or nothing bound. Okay, so I'm going to start with nothing bound. Okay, when nothing is bound to the head, that head will not release. That head will not come off. Okay, so what happens is ATP is going to come and bind. When ATP binds, it will release the thin filament. Okay? Now, we've got to cock the head. Right? We've got to cock the head, move it to a different position, I change the angle, and have it bind. Right? What happens to ATP to cause that? Yep, ADP, inorganic phosphate. Okay? So when that happens, it will bind, but now it's cocked, right? It's ready to push that thin filament. How do you get the head to push the thin filament?
Release it.
It releases it, right? So when ADP and inorganic phosphate come off, that head will pivot and pull the thin filament with it, right? So we're pulling the walls in, right? This will repeat as long as there is calcium and ATP. Right, so as long as you have calcium and ATP, this continues to cycle. ATP will come in and bind, that causes it to release. ATP will become hydrolyzed to ADP and inorganic phosphate. We will cock the head and it will bind. ADP will come off. The inorganic phosphate will come off. The head will pivot, moving the thin filament over and over and over again. Right? So you just keep shortening the sarcomere. Okay? How do we stop it? Let's come back out here. Got to get rid of acetylcholine. How do we get rid of acetylcholine?
The acetylcholine, A starts on.
Yep, acetylcholinase. Excellent. So we've got acetylcholinase, actually esterase. AMP is an enzyme, right? And what it does is it actually cleaves the acetate group from the choline group. It breaks that neurotransmitter in half. Okay? When we break the neurotransmitter in half, what happens to our channels? They close. Right? What happens to the calcium? It's going to be pumped back in. Right? And you need ATP to move it back in. Right? Because we're going to build up a large concentration. Anytime you're getting a gradient, a difference across the membrane, you have to have energy. So we're going to pump calcium back in. What happens to troponin? It will let go of that calcium. It's being pumped away. Right? What happens to tropomyosin? Then it's going to go back to blocking, and that will shut this down. Okay? So, when someone dies, you develop rigor mortis, right? And that is stiffening of the muscle, right? Why does it happen?
ATP, you don't use it anymore.
You don't have ATP anymore, so can you get rid of calcium? No. No. What happens over here?
It stays there because you don't have ATP.
You don't have ATP, so it stays bound and locked in place, and that causes the muscles to rigor, right? To contract and stay contracted. Okay? You guys okay with the process? I forgot what else I had up there. Types, right? So we talked about a couple of different types of muscle. We had slow twitch and fast twitch. All right? The speed, right? Slow twitch and fast twitch. What is the speed actually referring to at the molecular level? Right? So what causes, what is the protein that is actually responsible for causing a sarcomere to shorten? You only got two, actin and myosin, pick one. Which one moves? Myosin does. This is telling you the speed that myosin hydrolyzes ATP. You with me so far? It's how fast myosin hydrolyzes ATP. So if it hydrolyzes ATP really quickly, you remember those 3 steps that we just went through? Remember those? Right? ATP binds, ATP is hydrolyzed, ATP, the products are released. Bind, hydrolyze, release, bind, hydrolyze. If you do that really quickly, what's going to happen to the speed of shortening of the sarcomere? Really fast. If you do it slowly, what's going to happen to the speed of shortening the sarcomere? Slow, right? So when muscles contract slowly, what do you know about myosin? It's moving slowly. When muscles contract quickly, myosin is moving fast, okay? So that's what you're talking about. When you're talking about speed of contraction, you're actually talking about myosin and how quickly it cycles, okay? Now, all of that deals with ATP, right? Where are we getting ATP from? Okay? Slow twitch is fatigue resistant. Can you sprint a marathon?
Yeah.
Can you survive a marathon? By sprinting it, right? Doesn't work that well, right? Right? Fast twitch, fatigue quickly, okay? So, the idea with this is that the energy supplies are going to be different, right? Here, we're going to use oxidative phosphorylation, right? Oxidative means oxygen, right? Which is aerobic metabolism, right? Where does aerobic metabolism occur?
Mitochondria.
Mitochondria. Okay? Fast twitch uses anaerobic mechanisms to produce ATP, right? That's glycolysis. Okay? You remember when we were covering this, we said glycolysis, you make 2 ATPs for every glucose. Aerobic metabolism, how many ATPs per glucose? 36 to 38, depending on how you count them. Okay? Why is fast twitch going to fast twitch muscle fatigue more readily? Not enough ATP, right? You're making 2 per glucose. You're going to run out of that really fast, right? Okay. So you guys okay with how quickly they fatigue and myosin speed? for these? Okay. Which one is going to have more mitochondria? Slow. Right? Now, this is aerobic. What does that tell you about what you need to make ATP? Oxygen. What stores oxygen in muscle? Myoglobin. So in this type of fiber, you have lots of myoglobin because you need oxygen to make the ATP so you don't fatigue.
Is that why the slow muscles are more red?
Yes. Myoglobin is similar to hemoglobin. Both of them have iron, making muscle red. Right? When iron rusts, it turns red. Okay. All right. Now, tell me if we wanted to make as much ATP. Let's say we want to make 36 ATP. How much glucose would we need? How about over here? 18. Right? So how do we store glucose in muscle? What do we store it as? What polymer of glucose do you have? Starch or glycogen? Glycogen. Starch is in plants, glycogen is animals, right? So where are we going to need more glycogen? Where do we need more glucose maybe? Fats, right? We needed 18 to make 36 ATP. So we needed a lot more glucose. We're going to store glucose in glycogen. Do we need myoglobin over here? No, we don't need the oxygen. Do we need mitochondria? We're not eliminating them all, but do we need a lot of mitochondria? No. Okay? Fast twitch muscles, the way they work is they build tension rapidly and then stop because they fatigue. Right? What would a slow twitch contraction look like? Right? Not as quickly, not as powerful, but can be sustained for a long period of time. Okay? So, you should be able to, right, tell me the different characteristics of fast twitch and slow twitch based on how they work. Right? You should say fast twitch don't have a lot of mitochondria, they don't need myoglobin, you have to have tons of glycogen. They're going to fatigue quickly, they're going to build up lots of tension, and then they're done. Right? That's your gastrocnemius muscle, your leaping muscle.
That's when like creatine phosphate and everything comes into play too. That's just energy.
Right. Creatine phosphate. Right. Creatine phosphate is an energy storage form. It's one step. You pull the phosphate off and put it on ADP, you got ATP. One step, you're ready. Okay. So that is an energy storage form. All right. You guys okay with this? Right, and then we did different types. We did like isometric and isotonic contractions. Isometric, iso is the same length, right? It won't shorten. Isotonic does shorten. And then we did tetanus, incomplete tetanus, complete tetanus, right? And that was just when you get a signal, you can still see it. That's incomplete tetanus, complete tetanus. Can't see individual signals, right? You produce the most power with complete tetanus. Have you guys heard of someone getting tetanus? Lockjaw? Your muscles stay contracted. All right, so you guys, we can look those up if you need help with those. All right, what else you got? Did I get your question?
Does she make like a difference there? Like the ones that produce milk and like the cells in the breast, how do you produce the milk? What is the milk?
CNS or PNS? Okay. What do oligodendrocytes do?
So put the myelin sheath, right?
They make the myelin sheath. So they're going to myelinate neurons in the central nervous system. Right? They're going to myelinate neurons in the central nervous system. What is a ganglion? Cell bodies. Are they located in the central nervous system or the peripheral nervous system? Yes. CNS. Right? You remember the dorsal root ganglion, then a chain ganglion. You were looking outside the brain and the spinal cord to see those. Right? Astrocytes, CNS or PNS? CNS. What do astrocytes do? They've got one little process wrapping around a blood vessel, one little process wrapping around a neuron. What do astrocytes do?
Blood-brain barrier.
Blood-brain barrier.
There we go.
Right? They're going to regulate what comes out of the capillaries and what goes into the neurons. They are going to make a blood-brain barrier. Some things can pass, some things cannot pass. Why it's really, really difficult to treat infections in the brain, right, is because you have that blood-brain barrier. Leukemia cells hide out in the spinal cord in the brain to get away from the chemotherapy. That's why chemotherapy is actually injected into the meninges to get to those cancer cells, okay, because of that big barrier. Ependymal cells, CNS or PNS? CNS. What do these do? They're going to line the hollow parts and they make cerebrospinal fluid, right? If they're lining the hollow parts, they are on the ventricles. What's contained in the ventricles? Cerebrospinal fluid. Okay. Schwann cells, PNS or CNS? What do these do? Myelin. Right, so they are going to myelinate neurons in the peripheral nervous system. Okay. What about nerves? What are these? Collections of ganglion or collections of cell bodies. Nerves are going to be a collection of axons. Are these PNS or CNS? PNS. Right? Cranial nerves, spinal nerves were all PNS. So the nerve part of that, PNS. Okay? What are collections of axons in the central nervous system called? Tracts. Corticospinal tract. Right? Remember all the tracts that we talked about? Those were all the ones that were running down the spinal cord. Alright, so make sure you review cell biology of the nervous system. Some people really struggled with that question as well on your exam. Anything else from the exam that you had trouble with? Anything, other topics that you had trouble with? How do you calculate the refractive power of a lens? Calculate the refractive power of that.
Is that a 0?
1 0.
Okay, 1 0, okay.
1 0. What's the equation?
Negative.
1 divided by the focal length. Where it comes to a point, we've got a virtual focal length here. So we have a negative, right? What are the units? Diopters. Okay? What type of lens is this? Divergent. What condition will it correct for? Nearsighted, which is called? Myopia. Okay? When someone has myopia, is the image in front, being focused in front of the retina or behind the retina? In front. Okay. What cells are responsible for colored vision? Cones. Where are those typically located? Fovea, right? Where you have your most accurate vision. What light do they function best in? Bright light. Okay. If you are looking at something in your left visual field, where does it end up in the visual cortex? Right side. Even though it's going into both eyes, remember how we had those tracks that cross-eyed and some that didn't cross-eyed? Right? What does your visual cortex look like? You're going to map out the visual cortex. Okay. It's going to look like the retina. What about the fovea? Fovea's going to be big. You remember we talked about areas of convergence? Was there areas of convergence with the fovea? Okay. You guys are going to have to go study the special senses. It is a third of your exam. It is a third of your exams. You've got to go study that. All right? Make sure you look at it. All right? So you remember the retina. Talk about the fovea. Fovea, most accurate vision, right, occurs there. Right? The reason that it's most accurate is you have one ganglion cell for every cone cell. If the cone cell gets a photon, that information will go to the ganglion, which will go to the brain. You know exactly which cone cell got that photon, right? Received that light, right? Out here, if this cell receives a photon of light, right, it is one of 180 cells that are feeding into one ganglion. You don't know which of the 180 received the photon. You don't know. That's not accurate vision, right? It's one of 180, okay? This is why that fovea is so good at accurate vision. That is why it's so good, right? If someone's doing, like, if someone is a neurosurgeon, do you think that they're looking out of the corner of their eye when they're trying to operate on you? No. Dead center, right? Right in front of you. All of it's going to the fovea. 1-to-1, right? One cone cell to one ganglion cell, right? You're not mucking up the signals, okay? Out here on the side, peripheral vision, you don't have accurate vision, right? You don't have, if you're looking at something that you want to be able to see, you look at it right in front of you. You don't look at it out of the corner of your eye, right? What kind of cells are typically out here at the periphery? What type of cells are typically out at the periphery of the retina? Rods. What are rods responsible for? Gray vision, right? What light? Dim light. What else? Where do you detect rotational motion? I've moved on to ears. Where do you detect rotational motion? Semicircular. Linear acceleration, deceleration. Where do you detect linear acceleration and deceleration? Not spinning. Neutrophil, stacule. The vestibule. Neutrophil and stacule are linear acceleration, deceleration. Okay, What are the little rocks in your ears called? Starts with an O. Otoliths, the little calcium carbonate rocks. Why are those important in detecting motion? Yep, the rocks move at a different rate than you do, and then they're going to bend what? The hairs, right? So you have otoliths stuck in this little, remember when I talked about you're driving your car with a box of rocks in your lap, right? So you actually have like a gelatinous mass with these otoliths in it, and then you have hair cells, right? When you accelerate, these rocks move one direction. When you decelerate, they move the other direction. Okay? That's going to provide action potentials where the action potential is going to travel. Down the, which branch of cranial nerve 8? Vestibular branch of cranial nerve 8. You guys okay? How you guys feeling about this final? Is it coming together for you? Because I'm really hoping it's starting to come together for you. If nothing else, I'm hoping you're going to go study this a little bit tonight. Kind of jog your memory. All right, what else? Anything else?
What are like the different pitches down there?
Say that again?
Trochlear, you can hear like different pitches in different parts of the trochlear.
Right. So lateral low, medial high pitch.
Okay.
Of the temporal lobe.
Okay.
Lateral low, medial high pitch. Yep. And then intensity was coded how? This one's yours? Intensity. Frequency of action potentials. Right? So it's pitch, which area of the temporal lobe, how loud it is, frequency of action potentials. Yep. You want to do that again? I may not be able to draw it as beautifully, but I will try. All right. Here's the eyes. Here's the nose. Okay, with how? Okay, so we got light coming in from the top. Okay. I'm going to do left visual field. And I clip the guy's nose. As you can imagine, if I had more space, I would not do that. Okay? Now, the way that the ganglion cells run into your optic nerve, right? They're the long axons that are running into the cranial nerve 2, right? They're actually bundled. Okay? And they're bundled differently depending on whether you're on the lateral side or the medial side of the eye, right? The nasal side of the eye. This side and this side, again, are bundled differently, right? They're going to go kind of head off to the optic chiasm. This will actually cross sides, right? The lateral sides don't cross, okay? So these ganglion cells will come optic chiasm and stay on that side, okay? So we've got the left eye, the signal will cross sides. The right eye, the signal stays on the right side. So it will go to the right portion, right side of the brain, right visual cortex, right? If it's dead center, it's going to end up on both sides, right? But if it's in one field or the other field, it will end up crossing sides. Because of the way it's bundled, you have to do that because you've got a left eye and a right eye. So the nasal part, if it's hitting the nasal side of the eye, it's going to cross sides. Right? These cross sides. And that gives you the optic chiasm, optic cross. Did that help at all? So if it's hitting the nasal side, it will cross sides. If it's hitting the lateral side, it will stay on the same side. guys good? Anything else? Right. So again, I think there's about 40 multiple choice questions. There's an extra short answer question, so there will be about 5 to 10 extra credit points on this exam. Right, so we didn't do the quiz on the special senses, which is why I'm telling you to study the special senses, right? There's extra points with that. If you think I have calculated your course grade incorrectly, please let me know within 48 hours so I can go back in and double check before it goes to the registrars. But, so again, check your grades on Friday. Everything should be up by then. If you have any other questions, feel free to send me an email or you can give me a call, leave me a message if I'm not in my office. I'm happy to answer any questions.